So let's get started. So good evening, everyone. I already uploaded last two video lectures on the e-learn. So please do check if you didn't see before. That's number one. Number two, as you are working on the assignment related to BLAS, this is one place where you may want to. This is netlib.org. This is the place where you may want to keep checking for whenever you get a doubt on semantics, you should go here and check the semantics. And so the way these functions, it is based on Fortran. Fortran is a very popular programming language in the scientific computing community, and it is still popular. And, that's the first programming language I have learned in college. So we were taught Fortran at that time, and it's a very good programming language. Second, so this is one important resource you may want to keep referring to if you have any doubts related to the course assignment. And the next thing is now, we talked about caches, we talked about, so we have on any system, we have L1 cache, L2 cache, L3 cache, and beyond L3 cache, we have hard disk. And when we think of hard disk, we have two kinds of hard disk. Hard disks which are based on magnetic storage technology versus a solid state devices, SSD. They have different properties, read-write properties. And then beyond hard disk, you have remote storage. When we go for distributed systems, you may want to access data that is present on a different system. And the different system could be present on the same LAN, or it could be present on a different network. So as we keep moving away from the computer, from registers to L1 cache to L2 cache, L3 cache, to main memory, to hard disk, be it HD or SSD, to a storage on on a system which is on the same LAN, to a storage on a system which is on a different LAN but within the same data center, versus storage on a system which is located in a different data center within the same continent and across different continents. So, and all these things are quite common because, like, for example, as systems scale up and for reliability reasons, you may want to have one node in Europe and another node in America, so that if there is a war, your data is not lost, so you still will be able to access the data from a different continent. In all these things, the important thing here is, as you can see on the screen, these numbers, latency numbers, every programmer should know. I came to know about these numbers only last year, but so I don't want to do that injustice to you. You should know it the sooner the better. So L1 cache reference is 0.5 nanoseconds, and then a disk access is, you can see some million nanoseconds. So, or if you look at the main memory access, the main memory access is 100 nanoseconds. So when you compare 0.5 nanoseconds with 100 nanoseconds, that means main memory access is 200 times expensive than an L1 cache reference. So if your data is present in L1 cache versus your data is present in the main memory, your program can potentially run 200 times slower. So that's a very big deal. So you really have to optimize your program so that you will be able to, so that when you access the data, it is available on L1 cache or L2 cache, or at least in L3 cache. You should try to check. And also you should see there is the cost of mutex lock. Yesterday we were talking about, two versions of the code. In one version of the code, the number of times you take the log when you are trying to accumulate something into the variable total, the number of times you take the log is proportional to the number of iterations or the number of additions you are making to the total. Then versus another version where you do addition separately and finally bring them together. So mutex is a very expensive operation. Okay. So keep that in mind. So yeah, these numbers gives us a sense, but so this is a this is an alternate way of visualizing this. So if you see here, this, if I am right, no, this 100 on the first column, if you see that 100 nanoseconds, no, this on the top you have 1 nanosecond, which is an L1 cache access time, and in the bottom we have 100 nanoseconds, which is a main memory access time. And yeah, so please keep that in number, in your memory or ready reference. But what is important is this humanized latency numbers. This is interesting. In order to give a sense of how these numbers compare with each other, you should look at this, what is called as a humanized latency numbers. So what it means is if L1 cache reference is equal to 1 heartbeat, then mutex lock is equivalent to making a coffee. Okay, so you can see the amount of work you can do in making a coffee versus your 1 heartbeat. And main memory reference, again, if L1 cache reference is equal to 1 heartbeat, main memory reference is equivalent to brushing your teeth. Okay, that's the time. And if the data is present remotely, then it's like equivalent to half day of work over a 1 Gbps network. So that means when you're doing distributed computing, there is data that is present on a different node. If you want to go and access that node, then it's equivalent to yeah, so having lunch at the end of the day. And SSD access is normal weekend, and then if it is HDD access, is there anything for HDD access? Not sure. There is one thing which is very interesting. Disk seek, yeah, disk seek happens in a HDDs because there's a read-write head which moves. So if your data is present in L1 cache, it is equivalent to accessing, it's equivalent to 1 heartbeat, and you compare it with the data that is present in the hard disk HDD, where you have to make a disk seek, it's equivalent to a whole semester in the university. Okay, that kind of puts the scale. In order to get an intuition about these numbers, these humanized latency numbers are very, very, very useful. Okay. And then decade, if you want to go to a different data center and access, Panchayatla, it's okay. So yeah, if you have to go to a different data center in a different continent and access it, then it's time to take no, to finish a bachelor's degree. Okay. Great. So anyway, so keep these things in mind. I will post this link also, or you can search it, you will get it. But these numbers should always be there when you are optimizing your system for performance. Okay, these numbers should always be there when you're optimizing your system for performance. Okay, so now with this as a background, and let's see. I will briefly review our discussion from the last class. Last class, I'm not completely satisfied. So I thought I will quickly review the discussion from the last class, and from there we will take it forward. So the first area is, let's look at our matrix multiplication to start with. Okay, so what we would like to do is we would like to multiply. So these are two matrices, and some bit of notation also I will try to say. So in all the benchmarks, no, not the benchmarks, the BLAS routine signatures that you are seeing, the BLAS interface that you see, M always refers to the number of rows, and this is M by K, and this is K by N, and what we have is this is M by N. Okay, so there we always use capital letters in the BLAS API. That's what we are looking at. So this is what we have. And whenever we are iterating, we use variable I to iterate against this dimension, and we use variable J to, not J, this is P. We use P to iterate this dimension, and we use variable J to iterate this dimension. So in other words, if you see I belongs to, this is, although I am putting it as a real thing, we just take integers. Are we still on Zoom, or is it got disconnected? Disconnected? No, it's there. So J belongs to 0 to, let's use first P. P belongs to, so of course we use, it's only integers, 0 to K. J belongs to, this is what we have, and all and only integers. Only integers in the interval. Okay, so now let's take a look at GEMV. So matrix vector multiplication. So GEMV is what we are looking at. We looked at two versions. I will quickly recall those two versions that we have. So we have M by K. This is a K by 1, and what we get is M by 1. So here we look at two versions. The first version is the dot product version. The other version is the AXP version. In the dot product version, what we do is, the first element here in the product column vector is obtained by taking dot product of the first row vector and the column vector that we have here. Okay, we take the dot product of this column row vector and the column vector, and we get the first element of the product column. And in order to get the second element here, we take this second row, and then again we take the dot product with this column vector, and we get the second. So this is what is called as a dot product formulation of matrix vector multiplication problem. So here, if you see, we are generating the elements of the product column vector, one element after another. So we can say the outer loop consists of, for I is equal to 0 to m minus 1, because because we are rendering this column vector, m by 1 column vector. So we say for I is equal to 0 to m minus 1, and inside here we want to do the dot product. Okay, and if we kind of expand, ideally speaking, in your implementation, you may want to use the dot product Rayleigh's implementation that you already have when you are working on BLAS level 1 routines. But just here for the sake of clarity, so what we do is when we take the dot product, we go along this dimension and we go along this dimension, right? So what we have is for P is equal to 0 to K minus 1, you do the dot product computation here. Okay. The code may not be exactly right, but what I want to see is the order in which we are having the loops. So here, the signature for the dot product formulation is I followed by P. Okay, that is, we first follow the I dimension. Outermost thing is the I dimension, and the innermost dimension we sweep is the P dimension. And if you are looking at AXP formulation, so now you take the AXP formulation. Let's let me use maybe a different color. So here we take the same, and we have A naught to A K minus 1, and we are multiplying it with this matrix, with this column vector, X naught to Xk minus 1, and this is M, and this is K, and this is 1. So here, what do we do? So the dot product here, the column vector here is nothing but sigma xi ai, I is equal to 0 to K minus 1. So this is the product vector 1. And what is the AXP formulation? The AXP formulation is y is equal to alpha x plus y. This is the AXP problem. So now you can see why the AXP problem is defined in such a way, because if we don't have this accumulation, then we will not be able to use the underlying AXP routine in order to do the JUMV, in order to solve the JUMV problem. This accumulation is important. If this plus y here is not there, you will not be able to use it. So it's very essential that AXP is defined in this way, so that you can use it as a subroutine to solve the AXP problem, to solve the JUMV problem. So here, now what is the code? What is the outer loop here? So we first take this vector, and then you accumulate it into the vector y, and then you take the next vector and you accumulate it into vector y, so on and so forth. And how do you accumulate? While doing the process of accumulation, you scale it by the corresponding xi value. And so this is equal to, how does the loop turns out to be? For P is equal to 0 to K minus 1. For P is equal to 0 to K minus 1. That is, we are going through one column after another column of the matrix A, and that's what we are trying to do. And once we take a column, we want to multiply it with the corresponding xi value. Okay, if you pick column A0, we want to multiply it with x0. And if you pick column A1, we want to multiply it with x1, so on and so forth. And so during the process of multiplying x0 with A0, we have to sweep the I dimension. So the inner loop looks like, for I is equal to 0 to M minus 1. This is how the inner loop looks like. And then there is some computation here. So the signature for AXP JUMV computation using the AXP formulation is Pi. The outer dimension is P, and the inner dimension is I. And these two formulations are important for us, because when you are multiplying matrix A, so this is the table that we have seen, which summarizes the story nicely. That is, we could be working with matrix A or matrix A transpose, or the matrix A could be stored in row major form or in column major form. If you are working on, this is a JUMV problem, and if you are working on and if you are working on the matrix A with row major, the best formulation is the dot product formulation. And the reason why dot product formulation is good is when you are accessing the row vectors, it has good locality properties. Okay, so you want to use a dot product formulation here. But let's say if the matrix A is stored in a column major fashion, just like in Fortran, matrices are stored in column major fashion, in which case you may want to use an AXP formulation to solve the problem. And the storage just changes if you're doing computation on A transpose. So what you have is no, in the library implementation for you in the Jambi problem, you have two implementations. One is a dot product implementation, and another is a AXP implementation. And if you see that BLAS API, there are a couple of things you will see, whether you are working with a transpose or whether it's a row stored, whether the matrix is stored in row major or column major fashion. So you use conditions and check, to see whether you want to invoke the DP version or AXP implementation. And that gives you the best design. Okay. Are you all with me here? Great. So in terms of parallelizability, is DP better or AXP better? If can I, in the DP formulation, is it possible for us to parallelize the outer loop? Can we parallelize the outer I loop in the DP formulation? Because it's very simple, right? This is the product matrix, and in this product matrix, let me use a different color. You can know these different threads can compute different segments of the product vector. So if you, it's very simple. So you just in this particular case, if you know the value of n, the dimension, you can use a static scheduler, OMP scheduler, and the value of n could be the number of iterations you want to give a thread. You may just want to equally distribute them across all the available threads. So here, this is a very simple. Okay. How about the second formulation? Can you parallelize the outer for loop in the AXP formulation? Y is used again and again. So one way of looking at it is, you may think it is possible because like for example, this is the summation that we have, right? Sigma I is equal to 0 to k minus 1 xi ai. You can divide this summation into, let's say if there are 10 threads, you can divide this summation into 10 parts, and each of the threads can do the summation separately, and finally it can be accumulated. But there is one small catch here. What is the catch? Sorry? Yeah. So what happens is, all different threads, if they are trying to modify, let's say, y of 10, okay, y of 10 is y is a vector, right? So this product vector is obtained by a linear combination of different column vectors. So so if you take a particular thing here, different threads will contribute a value to this particular position in the column vector, and we need a mutex to update it properly. Okay, or we need to specify I don't know, something else to do it. Otherwise, we will get into trouble. Okay, I see one disadvantage of the AXP formulation, but I think, is there a clever way of getting around it? Sorry. It depends on how you parallelize, because if y is a shared vector between the product column vector y is shared across all the threads, all the accesses to y needs to be synchronized. Yeah, of course, that's a strategy we can use. So each thread will have its own y, and and then finally we put it together. Just the way we do for scalar variables, we can do the same here also. The only thing is it will kind of increase the memory accesses by a bit, because if you divide it into 10 threads, then you have to scan the memory 10 more times for the accumulation operation. So that is a problem. Yeah, that's true. That's not good multiplication, because at a we want to use FMA instructions. Oh, okay, okay, I see. The number of memory access is increased. That's the only problem. You're putting pressure on the memory band. But don't we lose out on using FMA operation? Is there a FMA at all? Yeah, there is. That's the only thing that I'm thinking. But anyway, think about it. So you see the challenge here. Any other ideas, suggestions, questions here? Okay. So let's move on then. So this is the summary for JMV, and the important thing is how whether to use the DP formulation or AXP formulation in order to increase the memory locality, and that's what we are looking at. Okay, and as we can see, in order to increase memory locality, if you use the AXP formulation, at the face of it, it looks like we are losing out on parallelism to some extent. But I guess we may have to figure out some a way to solve this problem. Okay. So now let's get going. Yeah. So now we look at the more complex matrix vector matrix multiplication problem. So which is so before I move on. So any questions on matrix vector multiplication? All good? Okay. Now let's look at GEM. So again, we will look at multiple versions of GEM, and so this is M by K, this is K by N, and this is M by N. What is the first version usually that we study in our programming course, or is in order to compute I comma jth element here, you take the ith row vector and jth column vector, you take the dot product of these two and you get the I comma jth entry here. So this is the dot product formulation here. And what we do is we usually generate all the elements of the product matrix, the first row followed by second row, followed by third row, so on and so forth. So what we have is for I is equal to 0 to this is n minus, yeah, I is equal to 0 to m minus 1. And then you fix the row, and for j is equal to 0 to n minus 1. And what we have is something like C of ij is equal to 0. And then we say for p is equal to 0 to k minus 1. C of ij is equal to C of I comma j plus A of I P times B of PJ. This is the usual code. And if you see this, this what we call it as IJP formulation. IJP formulation. IJP formulation of the matrix vector multiplication. And here we are using dot product, right? So what we are doing is we are picking in order to compute underneath, we are using dot product. We are taking the dot product of ith row vector with the jth column vector, and when we take the dot product, we get the I comma jth element of the product matrix. So this is a dot product formulation. So when you write code this way, so once we pick these two, so you should just use the underlying DP routine in order to do the computation. The underlying DP routine you may have already optimized somewhere. Okay, you may have spent a lot of time trying to optimize it. You just use that formulation and and also keep in mind, if you are trying to port your BLAST routines to a different machine, and if you are not using this underlying DP routine, and when you port it to a new machine, if you optimize your DP, then it's not automatically translated, that performance is not automatically translated to your matrix multiplication problem. So using the underlying dot product is important, and all the complexity in the signature of the dot product is because of that domain. Because otherwise, why the signature for dot product should be very simple, right? It's n and x and y, where these are all n is the vector length and x and y are the base addresses of two vectors. But you want to use dot product as a subroutine in a different place. So, and especially if you want to use dot product as a subroutine in matrix multiplication, so you have to see that, that increment x, the stride for the row vector axis is 1, whereas the stride for the column vector axis is n. And because of that, you have in inc x and inc y in the BLAST dot product signature. So in order to accommodate for these things, the signature gets very complex even for BLAST 1. So now let's see what kind of performance that we get here. Let me stop sharing my screen. I should. Okay, where is my code here? MML IGK. So this is what. So here you can see in this code. So outer I loop, outer J loop. Inside, I am calling this S dot routine. And just to see, here we are using S dot, right? Let's go to where is S dot underscore. This is dot.c. So let's start here. We want to analyze the matrix multiplication problem's performance. So now there is no parallelization or nothing. So make ML IJP. Let me not use minus G option. You can see we are getting around no vectorization, no parallelization. We are getting around 3.5 gigaflops, 3.3 gigaflops per second. Okay, so let's close this one. And now what we will do is we will go to S.C and we enable vectorization. So when we enable vectorization, we are getting some, yeah, it's not even much. Yeah. Stop. Let's save this one. Let's again do this. You can generally see as the matrix size increases, the performance goes down. Yeah, it is 3.39. So this is without vectorization, we are getting 3.5, 3.2, so on and so forth. That's the range. And with vectorization, let's see here. So actually, this is a bit of a pity that with vectorization, what we are getting is very small because I didn't put in sufficient hard work to see what is going on underneath. Okay. So anyway, broadly, you can see, like for example, here for around 200 matrix size, we have 3.22 gigaflops or 3.2 gigaflops, and here we get 5.5 gigaflops or something like that for matrix size of 200. As the matrix size increases, what happens is the problem becomes memory bound and the performance goes down. Okay. So that is one issue. The other thing is, as I said, even in the best possible case, consistently I am seeing with vectorization, the gigaflops is just increasing from 3.5 to 4.5 or 5, which is not quite satisfactory because if you are using AVX512 instruction set or no, AVX512 is not possible here. If you use a 256 bit AVX2 instruction set with floating point numbers 4 bytes, that means 8 floating point operations we should be able to do in parallel, but we are not getting that kind of performance. That means there is still scope for improvement, but we are not using that thing. So what is it? Do you remember the option that we have to use for AVX? Can someone tell me? Minus X, AVX? Capital code. AVX2 or core, core AVX2. Will this work? Yeah, it's not. It's okay. I think that's what approximately that's what we are getting. Okay. Nice. So if someone wants to do a side channel attack on my machine, it's easy. Whenever I run some workload, immediately the machine starts making sound. Fan and all, everything goes up in my. So now, so that's a way to do some attacks on our system, side channel attacks. Anyway, so now, what is the next formulation? Yeah, now let's go here to IJP, and let's say we want to parallelize the outer for loop. Okay, let's parallelize the inner for loop to start with, and then see what happens. So we are parallelized, vectorization is enabled and inner for loop is parallelized. With inner loop parallelization, we are getting, let's say, around 15 gigaflops of performance. And it is going really bad as the matrix size increases, again, because there is a lot of memory accesses are happening and the system, the performance of the system collapses. Okay. What is the size of the matrix if it's a 1300 dimension matrix? I'm using a square matrix. 1300 times 1300. What is 4 bytes? What is the size of the memory? Is it in MB, GB? Can you quickly use Python and tell me? 1300 times 1300 times 4, 6 MB. Just 6 MB. For 6 MB itself, it starts crying. Okay. Bit surprised. Are you sure it's only 6 MB? No, 1300 is no, it's not the case. No? 4,000, 1,000 is 4, oh, maybe. Yeah. Okay. So check on that. So now let's say, yeah, we can do export OMP underscore threads. You want me to do it? Okay, let's do it. Export. I have bigger agenda today, so OMP underscore threads is equal to 2. Yeah, instead of whatever that 18 gigaflops, there is some decrease. Sorry? Oh, it's better for, interesting. Very interesting. So what could be happening when there are all these threads are is one, yeah. So one thread is getting the data it wants and the other thread is evicting the data. So there is lots of misses happening there. You understand there is a cache contention. The same cache is being contended by all the threads. And it's like this, if you have some 6 plates and 20 people have to eat food using the same 6 plates, you have your dosa. Before you eat your dosa, someone throws it out and they want to use it for their dosa. So all the time, what do? You keep looking for plates instead of eating food. So that's what happens here. It's a very good experiment here. So now one thing, let's try to do outer loop parallelization. Now we did inner loop parallelization. Let's do outer loop parallelization. How should I make it to the number of threads again back to 12? I should compile the program also. Yeah. You see around 30 gigaflops if we do outer loop parallelization. And inner loop parallelization, how much we got before? Yeah, we got around 15. And with outer loop parallelization, we are able to get bigger gigaflops per second. Are you all with me here? That when you are trying to parallelize, outer loop parallelization gives more work for each thread. Okay. And inner loop parallelization, and also the other thing is the number of times the threads have to sync. So here, if you look at this code, when we parallelize the inner loop, so after all the iterations of the inner loop are finished, all the threads have to wait. There's a barrier that will be there. And then again, we go for I is equal to 1. And then again, the next cycle of parallel execution. So if you compare the outer loop parallelization with inner loop parallelization, so where is pen? So here, so you keep going like this. In the outer loop parallelization, you go let's say 12A, T0 to T12, and they keep executing, and finally they merge here. This is outer loop parallelization. But if it is inner loop parallelization, the story will be different. So what happens is for I is equal to 0, so you split and and then again you come together, all these threads execute, and then again for I is equal to 1, again they split, and then again they work together. And then, so if you see when we want to do a barrier, at the barrier there will be a semaphore that will be present. So everything has to wait on that semaphore and everything is done. And then again they go to the next iteration. So this is the difference between the outer loop parallelization and the inner loop parallelization. Okay. Great. So now let's keep going. The next thing I would like you to look at is, so this is the simple, if you go back to our whiteboard. Yeah, this is the IJP formulation here, and we can do a different kind of formulation also. Okay, let's see what is that formulation. Okay, so this is the case. So now let's start here. We will see two different formulations now. So this is your matrix. This is your matrix, and you are getting this matrix here. So yesterday we have seen one way of looking at matrix multiplication is the first column vector is a linear combination of the column vectors of matrix A, and the linear combination is given by the first column vector of the elements of B0, B00, B10, so on, Bk minus 10. So you take a linear combination of these column vectors, A0 to Ak minus 1, as given by the coefficients from the first column vector of B, we will be able to render the first column of the output matrix. And then we can render the next column of the output matrix, so on and so forth. And when we do this, when we are rendering one column at a time of the output matrix, what will be the outermost loop? What will be the outermost loop? Can we say the outermost loop is for j is equal to 0 to n minus 1? Can we say that? Because the dimension of this is, remember, this is an m by n matrix. So we are rendering one column of the output matrix every time. Okay. So this is the story. So we go from for j is equal to 0 to n minus 1. And now, once we are inside, what we are doing here is a Jumvi multiplication. Yes or no? When we take the matrix A and when we take the first column, it's a Jumvi multiplication. And similarly, when we are trying to render the second column of the product matrix, again we are doing one more Jumvi multiplication, that is matrix vector multiplication. And in this process, remember, there are two ways of doing this. Yes or no? So one is the DP way and other is the AXP way. And when we do the DP way, what is the iteration? DP is IP. DP is characterized by IP and AXP is characterized by PI. So what happens is DP is characterized by IP and AXP is characterized by PI. So we get two versions of matrix multiplication. One is JIP and other is JPI. So these are the two different versions of the matrix multiplication. Does it make sense? And in this particular case, is it possible for us to parallelize the outer loop here for j is equal to 0? Can we do the outer loop parallelization? We can do, right? We can just render the different columns. This is one segment, this is another segment, so on and so forth. We can do it in this way, and so that different columns of the, we can chunk the columns of the product matrix, and each chunk can be rendered by a different tool. Okay, so now let's go here. Let's go to our stop share, and why is any description closed? IJP is done. We don't need S dot. Let's keep S dot here. Yeah. So now, what is PIJ? We'll look at PIJ formulation. Is there any code for me here? Yeah. I think I didn't write the code for where J comes first. I didn't write the code, so maybe I will leave it like that. But I hope you got the idea. The next version, for the next version, I have written the code. Just before I proceed further, does this make sense here? We are trying to render the columns of the product matrix, and every column is nothing but a matrix vector product. And when we look at a matrix vector product, there are two ways of doing matrix vector product. One is DP way, the other is AXP way. And the DP way gives to this a signature. This is the signature that we get when we do the DP way. And this is a signature that we get when we do the AXP. So here, you should use Jamvi formulation. Okay, so you should call, when you are writing your program, instead of writing this whole code again, you have to just call the Jamvi routine. This is a BLAST3 problem. When you're trying to solve a BLAST3 problem, use a BLAST2 implementation that we have already prepared, and you just, and that Jamvi, these two should already be optimized so that we can just use them. Okay, this is the summary. So now we go to the last way of doing matrix multiplication. So much for this problem, but it's very interesting. So this is what is called as an outer product formulation of the matrix vector multiplication problem. Okay, so let's look at this outer product formulation. In the outer product formulation, or what is called as a rank 1 update, so what we do is, we have a column vector here. This is an m by 1 vector. And then we have a row vector here. This is a 1 by n vector. And what is the product of this is nothing but it's an m by n matrix. Okay, this is an m by n matrix. Great. So what's the story here? The story here is this outer product formulation or rank 1 update. Again, it can be looked at in two ways. One way of looking at it is, you take every row here. Okay, this is, let's say, for the sake of simplicity, you can, let's call these elements as x0 to x m minus 1, and let's call this whole vector as y. Okay, in the first formulation that we have, the product matrix is nothing but x0 y, x1 y, so on up to xm minus 1 y. Okay, this is what is called as a row formulation. And in this particular formulation, so where we are trying to render one row at a time, what happens is, what we get is, for I is equal to 0 to 0 to m minus 1. Do you remember what is there's one blast one routine where we take a vector and multiply it just by a scalar? That is the most basic thing that we have. Something like y is equal to alpha x or something like that. This is the most basic blast one routine that we have seen. So you just have to call that blast one routine using the as a subroutine for I is equal to 0 to m minus 1. You just go ahead and okay. And here, when you do this, what will be the inner loop? The inner loop will be going from for j is equal to 0 to n minus 1. Okay. So I would call this rank one, this particular rank one update. This is what is called as a outer product or rank one update. This is characterized by the signature ij. The outer loop is I and the inner loop is j. Okay. And there is an alternate formulation for this. Okay, the alternate formulation is this. So you call this as y naught to yn minus 1, and this whole vector, you just call it as x. Again, this is an m by 1 by n. Then this is nothing but m by n. So what is the first vector here is m naught x, y1 times x, so on and so forth, yn minus 1x. So these are the column vectors. These two are the same. These two are exactly the same. It's just that we look at it in a different way. And when we look at this, what we are doing is we write the code as for j is equal to 0 to n minus 1, and for I is equal to 0, because you are rendering one column at a time. You pick a column and you render all the elements of that column. So because of that, the inner loop will be I and the outer loop will be equal to j. For j is equal to m minus 1, and you have the, and the characterization for this is ji. The signature for this is j. Between these two formulations, which one should you use? Which one should you use between the, you want to use an ij formulation or a ji formulation? Ij formulation is better, right? Because when you are rendering one row at a time, the locality will be better. The cache memory utilization will be better than rendering one column at a time, because the stride will be very large. Does this make sense? Are you all comfortable with these matrices and vectors in linear algebra? You did linear algebra course. Okay. Any questions here? Because we will be using this rank one update and go back and solve our matrix multiplication problem. So let's go there. Yeah, let's see. So you have a, so now this is again very interesting. M by k, k by n, and m by n. So now in the last, in the current formulation of the matrix vector matrix multiplication problem, we look at our matrix multiplication problem as like this. You take this column vector and you do this row vector. What it generates is, it will generate a m by n matrix. Okay, so let's call it as 0, 0 matrix. 0, 0 matrix means it is obtained by taking an outer product of the 0th column of matrix, first matrix, and the 0th row of the second matrix. And then you take this one, and then again you take all possible combinations of ij. Okay, so and then you take so not this, not all possible combinations. So now you go to the next column and you go to the next row, and then again you do this formulation. You take an outer product of this and outer product of this. You again get this this formula, this another outer product, and we keep adding them up. And how many will be present? How many terms will be present in the summation? K, because we take one column and then we compute its outer product with the corresponding row. So we will have overall K such things, and we have to add them. So if you see the time complexity kind of works out, because ultimately I think we will be doing n cube additions. Okay, overall n cube operations will be. This complicated formulation, does it have any advantage? This complicated formulation, does it have any advantage? Exactly. So the primary advantage of this approach is, once a column and row are used, you can completely discard it. Okay, that means we can compute our, if you can hold our, let's say, in the cache, if the matrix size is like that, if the product matrix can be nicely fits into the cache, this is a fantastic thing, because we don't need to, you just stream in the input data, you use it once, you compute it, and you store the, and if the product matrix is small enough to fit into at least L3 cache, then you don't need to go to the main memory, and all the updates will happen, and there you go. So we can potentially get great performance out from the system. Exactly. Yeah. For distributed computing, also this could be useful. Because if it's a very large matrix, you can split some rows and some columns locally, and finally do that. The communication cost across nodes will substantially go down. Awesome. Yeah. Makes sense. Good. Okay. So this is a very nice formulation, and let's see what kind of performance we get for this. And then again here, so now, what is the signature for this? So here, when you are trying to render, when you are iterating, doing this outer product between a column vector and a row vector, one after another. So the way the code looks like is, for p is equal to 0 to k minus 1. And when we are doing the outer product, remember, we can do it in two ways. One is the ij way and other is the ji way. Depending upon which way we are doing, we will get two kinds of matrix multiplication. One is Pij and other is Pji. Okay. Yeah. Yeah. So, of course, in order to put the final result together, there is, but if you do regular matrix computation, the same row you may have to keep transmitting it again and again when it is being accessed. Every node, the way I am seeing is, if the distribution is done in such a way where, like, for example, let's see, I'm thinking one way of thinking is, if the matrix is stored in a distributed fashion, like for example, let's say you divide it into 3 chunks, and you store this one, no, this P1, P2, P3, R1, R2, R3. What I am thinking is, if P1 and R1 are co-located with each other, does this help? then a lot of how much computation will be communication will be required in this particular formulation, because you take this one when you are let's see, when you take this one and you take the outer product, there is no communication, right? First column, and then when you are trying to generate outer products from chunk P1 and R1, there is no communication. Okay, so the communicate, and then similarly P2 and R2, when we are doing, again there is no communication. And similarly in the third partition R3 and P3 and R3 also there is no communication. And locally they generate matrices. You accumulate the sum of those three matrices locally, and overall the communication that is required is equal to the number of partitions times n square. I thought somehow that number will turn out to be less when we don't do this strategy. We have to work out the numbers. It also depends upon how the matrix is partitioned. So if you don't do it, and if you just blindly split the matrix, then you may end up using more communication. That's what I thought. But I think we have to work out the numbers. But this is a thought process I had when I thought, no, this could be better for distributed computing, because there is no local, everything is local. Finally, accumulation is global. XY, which facts? Entire matrix. Not, yeah, that's true. Every node will generate a square matrix. And again, it depends on if you do it, if you don't do this strategy, and if you have an alternate strategy, then how many times you end up sending the same node again and again to the. It's a good problem to think. What do we say? Is there any? What can you suggest an alternate strategy and see? Regular. If you just do regular, IJK computation, and let's see. This is the one we have. So we have to assume a data distribution strategy in order to kind of make some comment about it. Let's say for the sake of simplicity, let's assume in this particular case, you divide this matrix into three parts, P1, P2, P3. You divide it into three parts, R1, R2, R3. Then what will be the communication cost when we want to perform matrix multiplication using this partition strategy? Because the communication cost depends on the partition strategy, not only the algorithm, the partition strategy also. Okay, so just assume this partition strategy, and if you try to do the communication, and if you try to see P1 and R1 are present in node 1, so what happens is if the node 1 is trying to compute the top some number of columns. Anyways, try to do the math and see. The first bit should be this way, right? There is no such requirement. As I said, sorry. You have to multiply the columns with the rows. No, we are looking at a different multiplication algorithm. IJ. Okay. So we need to have a data partitioning strategy. That's the high level. Let's move on. We have 10 minutes and we have important things to cover. Okay. So we have these two things, Pij and Pji. Which one is better? Should we do Pij or Pji? What will be a good algorithm? Should we try Pij or Pji? That's the question. Which one has better locality? Pij has better locality, right? Because we are rendering row at it. Okay. Now let's go and check if it's really true. Okay. Stop. Share. Okay. Matrix multiplication. Pij. Great. So here I would like you to see that okay. Okay, it's fine. Let's see. As you can see, I would like you to take a note here. In this matrix multiplication problem, you can see the outer loop is P, okay? And in the outer loop, we are calling a this rank 1 update routine, that is S, which I have written in some other file. Let's see where it is. Yeah, I have two implementations. One is Sger. This is the place where we are iterating in ij form, and there is one more implementation where we are iterating in ji form. Okay. Great. So now let's compile this code. Are you with me here? Shall I go ahead? So what we are doing here in this matrix multiplication routine, we are iterating for p is equal to 0 to k minus 1, and inside we are calling a rank 1 update routine, where there are two ways, there are two implementation. One is ij implementation, other is ji implementation. Let's call both of them and see what happens. ij implementation. Let's try one. This is ji. So without parallelization, let's see what happens. I'm compiling both versions, and let's see what happens. So we are getting around, without using outer loop parallelization, we are getting around 8 gigaflops. How much is it before? In the previous version, IJK version, without around 4 or 5 gigaflops we are getting. If I use PJI implementation, you can see it is really bad because the locality properties are super bad and the gigaflops have gone really. Does this make sense? And now let's go and see Pij implementation. We will put a, yeah, we want to parallelize the outer loop. So now I have a question for you. So is this a parallelization right thing to do? Can I parallelize this outer loop here? How many of you think I can parallelize this outer loop? Forget about correctness, we'll just compile it and see what happens. Okay. So this is the highest gigaflops I could use on my system. Okay. But the problem is I was happy for a moment and I thought it's awesome, but there's a problem in this. What is the problem? 50 gigaflops I didn't get for any program actually. This is the first program I'm getting 50 gigaflops. And let's see how much I get for PJI. Yeah, there's still locality problem and it's not able to get over it. So what's the story? So when we are using this outer product formulation, and especially if the matrix size is like that, if the product matrix can nicely sit into the L3 cache, then we do really, really well. Okay, that's the summary picture here. Okay, but there is a problem in this formulation. There's a problem. The problem is the same as we have seen before. What is it? So here, when we parallelize the outer loop, what is happening here? When we parallelize the outer loop, let's say this part is done by thread T1 and this part is done by thread T2 and this part is done by thread T3. All of them are accumulating into the same matrix. And all of them, when they accumulate into the same matrix, there is a race condition. And because of that, the correctness will be lost. Okay, and of course, the way to do it is do the accumulation privately and do the final summation in a different. Okay, that is one way of doing it. So how much overhead it will add, we have to see, but it may not be much. But it's very nice to see that we are able to get 50 gigabytes per second, 50 gigaflops compute we can get is fantastic. Okay. So now I would like to take the last 5 minutes and conclude this discussion by taking this problem to the next level. So the next, usually what people will do in order to use the caches better is what is called as a tiling strategy. So if you have your matrix like this, and if you have your matrix like this, so you take this matrix and you take this matrix, let's say you split it into 4 parts, and the product matrix can be looked at like also as 4 parts. Like for example, this is A11, A12, A21, A22, B11, no, B21, B12, B22. Then like for example, this is given by A11 times B11 plus A12 times B21. Okay, so this is now we are doing a blocked matrix multiplication. We are blocking the matrix, and so blocking is a very, very common strategy. Use it for to enhance locality properties of a program. So like, for example, the original matrix, if you remember just now we have seen the PIJ implementation, it is very powerful because it uses the cache well. So the original, if after splitting this matrix into 4 parts, if this matrix can nicely sit into the cache, the submatrix can nicely sit into the cache, then it is fantastic because we will get a really good performance. But let's say if the submatrix cannot fit into the cache, what can we do? What can we do if the submatrix cannot fit into the cache? Yeah, so divide it further. So generally speaking, you can take your matrix and divide it into into a grid like this. And you take the product and the second matrix also, and you divide it into some. And when you divide it into this, the number of rows here should be equal to the number of columns here, the block columns, not the, okay? And you do it. And you want to do the split in such a way so that these tiles will nicely fit into the cache. And there is no easy way to figure it out. While there are some analytical methods, usually what we do is we can write a Python script and and you try the different values of B and find out what is the value of B, which kind of works out well. And this is what is called as an auto-tuning strategy. Like for example, in the reading exercise or in some place I mentioned Atlas. Atlas is a BLAS implementation. The property of the Atlas is if you install Atlas on my machine, it will tune all the parameters so that it runs best on my machine. And if you install the same on your machine, it tunes all the parameters so that it runs best on your machine. And this auto-tuning strategy, these are called as auto-tuners. That is where again, did you study AML course? No, AI course you may have studied. No? You can try out different search strategies to figure out what is the best set of parameters you may want to use so that we can get good performance on a given system. So when you install Atlas on your machine, it's just not some install, it tries out different things and tries to configure itself so that it runs the best. And it is important that you don't do anything else while you are running that system, because otherwise it will incorrectly configure itself on your system. Does this make sense? These auto tuners. So Atlas auto tuner is an example of it. Okay. So now we will look at a very simple version of this problem, and I will also show the implementation, and then we can conclude today's class. So in this simple implementation, so instead of completely tiling, what we do is this. Okay, we divide the first matrix into a collection of rows. Okay, the size of each row is B. Okay, if you see here, there are B rows in each segment. Okay, so this is still M, this is still K, this is K, this is N, and then we divide this into columns. And again, the size of this is equal to B. Let me use a small b here. This is B and this is B. And this is the product matrix. So in order to get the first B by B block in the product matrix, this is a B by B block in the product matrix. You take this, you take the first B stripe. This is a B stripe. This is a B stripe. You take the B stripe. What is a B stripe? A B stripe is a B by K matrix. Okay. And then again, this is a horizontal B stripe and this is a vertical B stripe. You take this vertical B stripe. This is K by B. So you take this horizontal B stripe and you take this vertical B stripe and you multiply this horizontal B stripe with this vertical B stripe and you get the top B by B part of your matrix, of the product matrix. Does this make sense? Okay. So what is the advantage of this? When we multiply this B stripe with this B stripe, the dimensions of the resulting matrix is B by B. So if this B by B matrix nicely sits in, if this sits in L3 cache or L2 cache or L1 cache, then what happens is you will get really good performance. Because you can stream in this row, you can stream in this column, you can stream in again next row, you can stream in this column. So you do the product of these two B stripe matrices, horizontal B stripe matrix and vertical B stripe matrix, using the implementation, PIJ implementation of the matrix multiplication problem. Does this make sense? You take this B stripe, you take this B stripe and give it to the PIJ implementation of the product matrix, PIJ implementation, and then you get this B by B matrix, and then you keep repeating again. So this is supposedly really good when we are, in order to utilize the cache better, in order to utilize the cache. So I have an implementation of it. Let's see. Where are we? What are you seeing on your screen? Whiteboard or desktop? Or I am not seeing whiteboard because Okay, I am on my machine. I'm using the reasonably complex. Ah, okay, got it. Any questions here before we move on? Does this make sense? The broad idea, you got it, right? How do you render the first B stripe, horizontal B stripe of the product matrix? So you take this B stripe and you go to the next B stripe, and then again you multiply them, you get the next block of the product matrix. And the whole idea here is by choosing the B stripe, the B parameter appropriately, the product block matrix can nicely fit into the cache, and the rows and columns of the source matrices can just be streamed. And if you can stream them fast enough and you can prefetch them fast enough, then that means you will have a very good performance. Okay. So now let's see. Okay. Just give me 5 minutes, yes, and then we will conclude today's session. Multiply, block multiplication is what we are looking at. Yeah, this is the code. If you see, I'm calling, I'm dividing the MB is equal to M by B. That what it indicates is, B is the block size. I'm defining it here. The block size right now I have defined it as 50, and yeah, so I'm iterating through the blocks and doing the block multiplication using the innermost thing, using SGMPIJ. Let me see here, ml pij.c. Let's see how this works. Make minus b ml block. Okay, let's see. So we are getting some 14 gigaflops, and are we using parallelization here? No. We are using inner loop parallelization we are doing, and maybe outer loop parallelization. Not sure how it works. Let's see. So we are not getting great performance. I have to see what is happening in the code. Just wrote it before coming to the class. But one thing we can try out now here is this. Let's see, PIG. Yeah. I see, I see. You have a point there. Okay, let's see how it goes. But it may stay around the 15 gigaflops. This is my guess. Yeah, that is. Yeah, we have to see what is going on here. Maybe I should keep this one. Yeah, so that is true, but most probably I'll get a segmentation fault. Let's see, just 1 minute. Yeah, this is doing an outer loop parallelization. So let's change the block size. Pragma. force. Just 1 minute. By changing the block size. By changing the block size, we are able to get 30 gigaflops. Awesome. Sorry. Yeah, sorry. I'm done here. Okay. Anyway, so please feel free to leave. So finally, what I want to conclude is, you can see the change in the block size from 10 to 50, and you can see the gigaflops change it from 10 gigaflops, 15 gigaflops to 35 gigaflops. Especially, you can see, as Balaram said, when the matrix size is 600, also we are able to get very good gigaflops with this change in the block size. Okay. Does this make sense? Overall, the whole story today, there are different ways of looking at the matrix multiplication, and everything has a performance implication, and that's what we try to study. Yes, please go. Oh, sorry. Because I think if you choose the right block size, the number of main memory references will go down. That's the only thing. If the block size is too small, we are not using it properly. Okay. If the block size is too big, then there are caches there's a cache contention. So when we pick the appropriate block size, then we get the best performance. Okay. I think that's all I can say. Okay, so that's all from my side on this one. I really want you to think about these problems and see, like how you can get good performance, and how the choices that you make and the algorithms will have impact on the parallelization strategies, locality, and all those things. So that is the summary picture. We'll stop our